Take a look at these two images. Can you tell the difference between them? I'll give you a hint. In one of them, there are images of cancerous cells, and in the other one, it's normal cells. My guess is, if you're not a trained professional, you likely can't tell the difference, or at least you're having difficulty, and that is completely normal. In fact, veterinarians and doctors, or other professionals who know how to distinguish between these types of images, have gone through specific training to do so, because it's not intuitive. And even for these professionals, they sometimes make mistakes, which can cause to misdiagnosis, whether it's missing cancer or improperly diagnosing it, which could cause stress to families of dogs, cats, or people. So how do we prevent mistakes like this due to human error? Well, we could remove human error. And while this is easier said than done, there are ways to do it. In fact, AI, or artificial intelligence, offers one possible route. Image recognition, a subset of machine learning, which is a subset in itself of AI, uses algorithms to differentiate between different images and predict the classification of images, such as containing or not containing cancer cells. Because of this, I decided to try to make my own model to differentiate between patches of cell slides containing metastatic tissue and those not containing metastatic tissue. I used the PatchCamelyon dataset, which contains patches of cell slides, and I used Python as the language for my code. I also used TensorFlow as the library and wrote my code on Google Colab, which is a platform on Google Drive to write coding notebooks. My first step in coding my model was to perform several imports to be able to use the libraries and modules necessary for my project. I imported TensorFlow, Keras from TensorFlow, the TensorFlow Datasets module, OS, and Inception v3, as well as input, dense, global average pooling, model, and sequential from Keras, which I used in building the architecture of my model. Next, as the PatchCamelyon dataset was one of the datasets already in the TensorFlow library, I was able to upload it directly and split it into training, validation, and testing sets. Once the imports were completed, I printed the information of the dataset from the TensorFlow library. To better visualize the image data, my next step was to use the TensorFlow Datasets show examples code to see a few of the images and their labels. Before being able to set up the model, I had to prepare the images in the training, validation, and testing sets, as well as the sets themselves. My first step in this process was to normalize the images through resizing them and normalizing their shape, so that their shape would all be the same and they could easily be fed to the model and compared in training. Next, I defined AutoTune, which allows TensorFlow to optimize the productivity of actions when applied and set the batch size to 16. To increase the speed of training in the second to last step, I used counter and applied it to dataset train, or DS train. I then applied some other functions to DS train. So I applied the normalize images function and set the number of parallel calls able to be done to AutoTune. So TensorFlow would be able to optimize for the best number of parallel calls. I then used catch to allow some of the data to be kept in memory so that it would be loaded more quickly in subsequent runs. Next, I shuffled the data randomly and applied the batch size of the training set to the variable batch size that I defined earlier as 16. Lastly, I applied prefetch and set it to AutoTune, which was able to increase the efficiency by allowing images to be prepared in advance while the GPU is running. I applied some of these same functions to the validation and test sets. Once the datasets were prepared, I had to build the model for learning. To set up the actual architecture, I created a function named createModel, with the parameter of image size, which was 96 for the images in this dataset. I then defined the variable inception, which represented the pre-trained model inception v3, and defined some parameters within the model. I also froze the inception v3 layers with layer trainable equals false, and I built the structure starting with the sequential model. Before coding the additional layers into the model, I used model add to include inception v3 and global average pooling 2D, and set the expected shape of the input to the shape of the data. Next, I listed the dense, batch normalization, and drop layers before connecting each layer to the previous one so that they would be in order. Lastly, I defined the output as the final dense layer and set the model inputs and outputs to finally return the model. To view the architecture of the model before running it, I created a code block to print its summary. The last steps before being able to train the model were to compile the model and set its parameters, as well as define the variable callbacks to enable the model to stop running early if the loss on the validation set did not improve after 5 consecutive epochs, which is a measurement for training rounds. As the last step before evaluating the effectiveness of the model, I had to train it on the training data and run it on the validation data to estimate its accuracy on the testing data and detect possible overfitting or underfitting. Lastly, to evaluate the accuracy of the model on the testing data, I ran the model evaluate function. In the end, I achieved an accuracy of approximately 80% on this model, which was similar to the accuracy of Geert Litjens, who achieved an accuracy of 85.63 on the same dataset and who has published papers in the field. For this project, I experimented for over 7 hours by just changing the parameters of my project to try to get a better accuracy. I tried adding and removing dense, batch normalization, and other layers, as well as changing the parameters of the dense functions and changing optimizers as well as learning rate. And in the end, I learned that the models that are often praised the most in mainstream AI media are not necessarily the ones that are best for your specific project. It really depends on the field you're working in and the type of data that you're working with. To achieve a better accuracy, I could have tried using the Chameleon datasets, which was my original plan. The Chameleon datasets are similar to the patch datasets, but the images are larger as they're not just patches of images of cell slides. They are complete images of cell slides. Most people who have used that dataset and achieved a high accuracy in the 90s have had to transform those images to take subsets of the image and transform those subsets into parts of the dataset. Unfortunately, I experienced difficulties loading the Chameleon datasets onto Google Colab as my RAM ran out almost instantly whenever I tried uploading the dataset. So I had to use the smaller dataset. I will also admit that for this project, I did get Colab Pro to get double the RAM and be able to upload the full dataset. But in the future, to be able to upload even larger datasets, I'm trying to look for ways around directly uploading it, such as transforming it into zip files and unzipping them manually. I'm hoping this will allow me to bypass the RAM restrictions and work with larger and more complex datasets. For my next project, I will also be working on an image recognition project, but this time it will be with a veterinary dataset, which I have been looking for a very long time. I'm also going to be creating a UI or user interface for my next project, so I'm excited to share it with you all. Thank you and have a nice day.